Good morning. So today we're going to talk about properties of Bessel functions that will help us in computing expressions involving the Bessel functions. As I mentioned last time, it's going to be impractical to use this series format for any computation involving Jn of x. So let's see which types of expressions or properties we can derive related to Jn of x that will help us manipulate this function when we end up solving boundary value problems that lead to the Bessel equation. So make sure you have that handout available on Blackboard in front of you, the handout on Bessel functions. I'm going to prove a couple of those formulas, but from now on, you are supposed to use them directly in various computations. So I'll show you some examples and more will come later along the way. The reason I'm going to prove just a couple of those formulas is just to see how the mechanics works in terms of manipulating Jn of x. But obviously I'm not going to prove all of them because that's too much time spent on that path. The most important thing is to essentially make sure you know how to use these formulas, to practice with them. Think of these formulas like differentiation formulas, for example. So stuff that you have to use repeatedly in various contexts. So let me state the formulas that you will see. You don't have to write them down now because if you have the Bessel handouts in front of you, all of these properties are listed there. And let's see how we can prove some of those properties. So some of these properties, if you pay attention here, are related to either recurrence formulas, meaning that you have Jn of x in terms of Bessel function of the same type but of a different order, or properties involving the derivative of Jn of x. So kind of like differentiation formulas for the Bessel functions of the first kind. So let's start the first one. So let's say Jn of minus x equals minus 1 to the n Jn of x. So that's one property. Then a differentiation formula is x to the minus n Jn of x quantity prime. So if you differentiate this product, you end up with minus x to the minus n Jn plus 1 of x. So notice in this case, n has to be greater than or equal to 0. Remember, the n can be 0, 1, 2, and so on. So there's no such thing as a negative n in these formulas. And n is greater than or equal to 0, because if it's less than 0, this one makes sense. There is no j minus 1 of x. I mean, there is, but not in the, so not in the context we're going to deal with in our course. Okay, so we're going to deal only with Bessel functions of an order given by a natural number, 0, 1, 2, 3, and so on. Furthermore, there's a similar one here. The derivative of the product of x to the n Jn of x equals x to the n Jn minus 1 of x. So notice in this case, n has to be greater than 1, greater than or equal to 1, so that the lowest index possible is 0. X times Jn prime of x, this is equal to n Jn of x minus x Jn plus 1 of x, where n is greater than or equal to 0. There's another one for the same expression, x Jn prime of x, which is minus n Jn of x plus x Jn minus 1 of x. And again, in this case, n has to be greater than or equal to 1. Finally, there is a recurrence formula involving just Bessel functions without any derivative. So x Jn plus 1 of x equals 2n Jn of x minus x Jn minus 1 of x. Again, n has to be greater than or equal to 1. All right, so let's keep this in mind for a moment. There is another important formula involving an integral. We'll get to that in a short time. And let's see how we can prove some of these properties. So for example, the first one, let's say I want to show Jn of minus x is equal to this. And it just boils down basically to making sure you use this definition carefully. So if I start with the definition, Jn of minus x is the same thing if I replace x with minus x. Okay, so I'm going to copy the same summation. And I'm going to plug in minus x instead of x, and let's split that parenthesis a little bit, over 2 to the n plus 2k. And so notice now that I can actually pull out minus 1 to the n plus 2k out of this power. And minus 1 to the n plus 2k, I can split it further into minus 1 to the n minus 1 to the 2k, and then x to the n plus 2k. All right, so 2k is always even, right? So minus 1 to the 2k is always 1. Okay, so minus 1 to the 2k is equal to 1, always. And then I can pull the minus 1 to the n outside. And what's left is just, again, the formula for Jn of x. So basically, the effect of plugging in minus x for x was just the extra minus 1 to the n. Everything else is just like the same as if it was Jn of x. So that therefore, Jn of minus x is equal to minus 1 to the n Jn of x. This is kind of the mechanics that one does when proving these relations, but I hope it's clear that it's more advantageous to simply leave the answer in terms of Bessel functions. So as a rule of thumb, so basically let's write it as a remark here, because that's important. Basically, you want to leave the answer, no matter what you do involving Bessel functions, whether you differentiate them, integrate them, whatever you do, leave the answer in terms of Bessel functions, like without replacing them with the series format. So your answer will be in terms of J1, J0, J1, and so on, depending on the context. Now, you will see that in our case, we will practically deal mostly with J0 and J1, simply because the Bessel function that we're going to, the Bessel equation we're going to solve is going to be the Bessel equation of order 0. That's the one that pops up typically in the boundary value problems, the one I actually even mentioned in the beginning, right? So the one with n equals 0. So actually it might be practical to rewrite some of these formulas when n is equal to 0. So we'll get to that immediately. So how would you prove, for example, other formulas? Let's see. For example, let's assume we know already these formulas. So let's assume this one and this one is already known. Let's see. Actually, no, I'm going to actually prove these ones. Yeah, I'm going to prove these ones and maybe the last one. Okay. Let's actually do one more. Yeah, let's prove, for example, this one, and then we're going to assume this one and this one. So I'm not going to prove the second and the third one. I'm going to prove just one of them. So let's say I'm going to prove the third one. Again, just so you know, the proofs, I'm going to do them just for practice, basically, because you don't have to, of course, prove these formulas later. You just use them as they are. So let's show this third formula. Now, this is the derivative of a product of two functions, so nothing special besides just, of course, rewriting this in terms of a summation, and then maybe, then of course, using the power inside the summation. So x to the n Jn of x, let's replace again Jn with the corresponding series that you have here. So that's going to be x to the n summation from 0 to infinity minus 1 to the k over k factorial n plus k factorial x over 2 to the n plus 2k. Let's bring x to the n inside and combine the powers. So x to the n together with x to the n plus 2k makes it x to the 2n plus 2k divided by 2 to the n plus 2k. And then we're going to have to differentiate this stuff. Now, when we differentiate inside the summation, we only differentiate x to the n plus 2k via the power rule. So that gives me 2n plus 2k x to the 2n plus 2k minus 1 over 2 to the n plus 2k. All right, so pay attention now what I'm going to do. Notice that a factor of 2, if I pull the 2 out, this is going to be 2 times n plus k. It will cancel with a factor of 2 here. And anticipating actually what I have to end up with, you know, x to the n jn minus 1, let's actually remove, or, you know, factor out an x to the n factor out of this guy. So this is just algebra manipulation at this point. Let's do one more intermediate step. 2 quantity n plus k, I'm going to take an x to the n out of this power. And what's left, which is n plus 2k minus 1, I'll write it x to the n minus 1 plus 2k. Divided by k factorial, n plus k factorial, and 2 to the n plus 2k. Okay, so pause for a moment and look carefully what we end up with here. Notice I can cancel a factor of 2. So when I cross these 2 out, this will be 2 to the power n plus 2k minus 1, or n minus 1 plus 2k, just like the guy above. When I cross n plus k with n plus k factorial, the factorial is going to be up to n plus k minus 1. So remember, factorial means 1, 2, 3, up to n plus k. So the previous guy will be n plus k minus 1. So I can cross n plus k with n plus k, and you're left with n minus 1 plus k factorial. And this x to the n, we're going to move it to the outside of the summation. So let me write it over here. So I'm going to take x to the n out. And then let's rewrite what is left with the simplification that I just mentioned. So 2 cancels with this, n plus k with the factorial. You're left with x to the power n minus 1 plus 2k divided by k factorial, n minus 1 plus k factorial, 2 to the n minus 1 plus 2k. Again, slow down for a moment to convince yourself that what you see here is basically the definition or the formula for the Jn of x by replacing n with n minus 1. So if you look again at the formula for Jn of x, if I replace n with n minus 1 everywhere, that's what you end up with here. Which means this whole summation is nothing but Jn minus 1x. So we just proved the third formula in that list over here. Namely that the derivative of x to the n Jn of x is x to the n Jn minus 1 of x. This is one of those recurrence formulas that will be very useful later. And of course, I have to assume n is greater than or equal to 1, so that the lowest index here is going to be 0. So with that said, let's actually close this, end this part, and we're going to do this in the second part. We're going to prove another formula in that list. And actually, you know what? Let's actually do it. Yeah, let's actually do it in the same part, so that I have this list in front of me. Well, keep on debating actually with myself. Yeah, let's make a second part. I take that back. So I'll do the second part with the next properties. So stay tuned.